So this is kind of a crash course on redox, and I'm going to keep it open for everybody because other people can use it, and I'll probably want to use it for people. There's some things you should always have open for redox, and this is one of them. It's the standard reduction potential. You'll see it written this way, and you'll notice always the electrons are on the left for everything. Everything's written with something plus electrons going this way. Just be aware, this is all written as a reduction, and we'll discuss what a reduction is in a second. But you should always have this table open. How does this table work? Very quickly, anything on the top left that can connect with something on the bottom right will mean that if you mix these two items, a spontaneous redox reaction will occur. It doesn't matter if you know what redox is yet. Just keep that in mind. Anything as you go top left to the top right. So in this case, fluorine gas will react spontaneously with bromine, and fluorine will steal the two electrons. Whatever's up here will dominate the process, and it will force bromine to go this way. So that's the other thing I want you to keep in mind. If something gains two electrons, something else must lose two electrons. If you find fluorine gas here and you're looking for, let's see, bromine 2 over here, they will not react spontaneously when mixed together, these two substances, because they're on the same side. If you find something like bromine 2 and you want to see if it will react with fluorine ion, it will not react spontaneously because this is on the top right. If you find something on the right side and say, oh, I'm looking for to see if bromine ion will react with Fe2+, it will not react spontaneously because they're on the same side. Only things top left going down, even if it goes down 1. So fluorine 2 gas will react with a sulfate. Now, let's notice something. This is the other thing I want you to keep open. We'll go to this in a second. But there's several things I want you to always keep open when you're doing redox. One is the oxidation rules. It can be found in your textbook. It's also a quick summary that you'll find from a very good tutor online. This is missing a couple of the things from up here, but it's a good general thing to refer to or have open. And the other thing you should always have open is your periodic table, because you can say, hey, Peter, how does this relate to the periodic table, where I learned that metals on the left will give up their electrons to non-metals on the right, forming an ionic bond. Well, yeah, you're right. There's fluorine there. Where's bromine? Where's bromine? Remember we looked at bromine? There's bromine right there. What this tells you is situations where, oh, it's hard to figure out what would happen here, what the redox would be. But now from the redox table, I know that fluorine will dominate and take electrons for bromine. But I also want you to notice, just take a look at some of the things on the left here. Lithium, sodium, potassium, rubidium, barium, magnesium, calcium. And those will tend to lose electrons according to our old rules, right? Let's look at the bottom of the redox table. Oh, there's lithium, there's cesium, there's rubidium, there's potassium, there's barium, there's strontium, there's calcium, there's sodium, there's magnesium. Those are all the things we just looked up in column 1 and 2. These, and you might say, yeah, but they're written as getting electrons. Well, no. When something top left reacts with something bottom right, this forces the reaction to go that way. Be aware you're going to change this sign to the opposite. If it says negative 2.98, it's going to become positive, but we'll get to what these numbers mean later. So it's going to force it to go this way, and this way it's losing an electron. I'll get more specific to that later. But notice, there you go, column 1 and column 2 is up there. Notice up here, fluorine, column 7, halogen, right? Chlorine, halogen. Bromine, halogen. Mercury, let's look at where mercury is on the periodic table. Right? Mercury is a metal, and it's going to be right there, but you see it's on the right side. And this helps you for things that are questionable, where you don't know what the reaction is going to be. Silver, so you can see all the transition metals are right in the middle. Now be aware, this is not a complete reduction table. These reduction potential tables can go on for pages and pages and pages, because as you can see, they include various polyatomics in there. and how those will react with something. It's also totally related to what's called the reduction potential, in that we use these for batteries. For instance, a common one would be to hook up a little bit, well, maybe not silver, but a common one would be to hook up a copper electrode with a nickel electrode in and that's a copper ion to be fair. So you can have a copper electrode here in a copper solution. So let's say CuNO3 is a good one. And then you can run a wire over here, and you can put a nickel solid here, in preferably a nickel solution as well. And it's sort of divided by a thing called it's a bridge, a salt bridge, but we'll get to that in a second. And what will happen is this copper will exert a pull along this wire, and it will pull the electrons towards it, because copper's top left, it's going to take electrons. And it will pull one electron, and that's an exaggeration, but we'll get to it, off of this nickel. This nickel will go this way, and look, it'll pull 2 electrons, so we have to use 2 coppers. And this nickel will go this way in the process. The nickel solid will become nickel 2+, and it'll lose 2 electrons. So when the electrons are on the product side of the reaction, it's losing them. When the electrons are written on the reactant side, it's a reduction, it's gaining them. On the product side, it's losing them, it's an oxidation. All these tables are written as reductions, as gaining electrons, but in reality, when the reaction occurs, it forces this bottom one to go this way. And now we have to reverse that to positive 0.26 if we have to add up the potentials. And sure enough, we would add up the potentials, 0.52 and 0.26, and get 0.78 volts. And that is the potential current that's created by this battery. The electrons always come here. What happens to this nickel as it loses these electrons and becomes an ion? It dumps into the solution as an ion, 2+. What happens to this electron when it reaches this copper? This copper, which is floating as an ion, will come, this copper 1+, will come floating to this copper. It will grab this electron and become copper solid. It will grab on, and this electrode here will grow, and electrode here will grow and grow and grow as more copper is added. They use this process for electroplating and for creating pure wires and all sorts of things. One word of advice, you're going to see salt bridges, and you might say, what's the salt bridge for? If we didn't have the salt bridge, Ni would constantly dump into solution as Ni2+, based on this equation. And you'd end up with tons of Ni2+ in this solution until it gets plus, bigger charge, plus, bigger charge, plus. And that plus will eventually pull these electrons back and stop the electrical process. If you don't have a way of getting rid of that Ni2+, this battery will stop performing. The other point I want to make is the electrons only go through the wire, and the ions of the solution stay in the solution. So back and forth. This is how batteries were made. A spontaneous reaction between two metals with, usually in our cars, it's an acidic solution. And when it's run out, we start our car. We just use batteries to start our car. And then as our car runs, it recharges the battery. We'll get into that in a bit. When we're recharging a battery, we're essentially forcing the reaction to go against nature. But we'll get into that in a bit. So always have your redox tables open. Always have how to use it, top left to bottom right. And remember these words. Redox is simply the exchange of electrons. It occurs in a lot of chemical reactions, but not all. It does not occur in neutralization of an acid and a base. It does not occur in double displacements. It always occurs in single displacement and combustion. But for the rest, composition, decomposition, you have to analyze the formula. We'll get to that. Always remember this phrase, oil rig. Oil means oxidation is losing electrons. That's the way you can remember what oxidation is. Oxidation is losing electrons, oil. Rig, reduction is gaining electrons. Everything written in this table has electrons on the left becoming usually a solid on the right. That is all written as reduction, everything. And it's only when they react that the bottom ones get written as an oxidation, reversed. So oil rig, remember that. Reduction is gaining electrons. When something reduces, it is an oxidization agent. So it's kind of the reverse, because we don't want to say, oh, it's a reducer, or it's been reduced or reducified. We just like to say it's an oxidation agent. So it's the reverse of what's happening to it. It's oxidizing agent, it's oxidizing someone else. When something oxidizes, it is called a reduction agent. It is reducing something else. Whenever something loses electrons to something else, something must gain the exact number of electrons. They're not going off in space, and we're not getting electrons out of thin air. They're coming from something, so that's why we must balance all these redox equations using things like this. So that's one thing I want you to keep in mind, everything I've just shown you. The other thing you want to keep in mind is the rules you used in the periodic table still apply. These all tend to oxidize. They all tend to lose electrons. These all tend to gain electrons. It's just we need some more rules for unusual cases and things we can't figure out from the periodic table. But there are some basic rules you should always remember. When you're looking at something like H2O, and you need to figure out the oxidation numbers, H2O is perfectly balanced at 0, but their individual charges must add up to 0 in this case. We always consider oxygen as -2 except in peroxide, and there's another exception up here when it's with fluoride. Right there, OF2, it's considered +2. But generally speaking, that's the rule. Oxygen is -2. Well, there's one oxygen here, so it's one charge of -2. That means hydrogen must total to +2, because +2 minus 2 to equal 0. Well, there's two hydrogens. That means each hydrogen is +1. Generally, we don't have to figure this out because we have a rule for hydrogen. Hydrogen is +1 with nonmetals and -1 with metals. There's more rules specific in your book, but this is a good basic summary. Another summary is F is always -1. Fluorine's always -1. Halogens, so that's where fluorine, are usually -1, but they're positive with oxygen, with the exception of fluorine. That's why up here, fluorine is -1, and oxygen becomes +2. That's the exception rule. Fluorine is always -1. And then group 2, column 2, they're always +2, and group 1 is always +1. That helps us. And elements on their own, so if you see anything like O2 on its own or Hg on its own, they're 0. They have no charge. They're considered 0. If you see a polyatomic ion, let's say nitrate, NO3, 1-, the charges in here must add up to 1-. So we know that oxygen is -2. There's 3 of them, so its total charge is -6. That would mean nitrogen over here is usually +6. However, that would add up to 0. We have to add up to -1. That means nitrogen is actually +5 within this nitrate. In an equation, if you see nitrate on the left and nitrate on the right, you do not have to bother with this because nitrate is not being oxidized at all. However, if you see nitrate being broken up, being broken up like this, you do indeed have to calculate their individual charges, and then you have to say, okay, well, that's nitrogen in its natural state. That's a 0. This is oxygen in its natural state. That's a 0. That means this oxygen went from -6 to 0. How do you go from a -6 charge to a 0? When you can't add 6 protons, you can't add 6 protons. Protons don't get added and taken away. Only electrons do. Well, those electrons had to go away. The oxygen had to lose those electrons to go to 0. Wow, what's the losing electrons called? Oil rig. It's oxidized. Oxygen got oxidized here. Nitrogen went from a +5 to 0. One way to remember this is the charge went from a bigger charge to a smaller charge. It reduced. The charge reduced. But another way to say it, to think about it, is the only way I can go from +5 to 0 is if I gained 5 electrons to balance that 5 +5 to 0. Rig. Reduction is gaining electrons. That means I had to gain, that means nitrogen is reduced in this equation. Generally speaking, Going back to my table, if we were to look up oxygen gas uh, up here, we'd have to determine if this will happen spontaneous. My 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 instincts instantly tell me this is a bonded thing to a non-bonded thing, which means it would require energy, which means it is not spontaneous. More likely, this direction is spontaneous with a little bit of activation energy, because usually combining composition is a exothermic and decomposition is an endothermic. But that aside, we're just talking about how to use these oxidation numbers. So always keep your oxidation tables handy is my point. So those three things, keep your reduction handy with the handy meanings of what's reduction and what's an oxidizing agent and all that. Keep your periodic table open and keep your oxidation rules open. All right, let's move on. When we're doing something like this, I want you to be very aware that I am not going to do it. I am just going to teach you how to do it. Because the whole point of learning is like a baby learning how to walk. It's incredibly important you fall many times. Because if you don't fall many times, you will never learn. If you don't fail, you will never learn. So how do we do something like a question like this? Well, we clearly need to pull up our basic redox rules, but I also want you to keep in mind that you should keep the full one here just until you get going at it, and even do some examples in there. But for now, I'm going to keep the simple one, just because it's more compact. All right, let's have a look. We're trying to figure out which one's a redox reaction. What's the definition of redox? Somebody must oxidize and somebody must reduce. Let's look at this one and remember this rule. Elements by themselves or in their natural state are 0. So that's 0. Oxygen 2 is always as 2 because of Mr. Brinkelhoff. Remember Mr. Brinkelhoff. It will help you remember every element that occurs as a diatomic in natural state. They are all 0. So that's 0. Now let's look at our rules on the right. I can already tell you composition's probably going to, oh, looks like we have a little, I'm just going to pause. So we will now look at the charges up above. We can see that each hydrogen is -2 except in peroxide and with fluorine. But in this case, that's neither the case. So each hydrogen, oxygen rather, has a -2 charge. Carbon's not on our list. So it's why we have to check it out. Oh, I just got to turn that off, sorry. So that means if each oxygen is -2 and there's 2 of them, the charge over here is -4. For this, there's just one carbon here. For this is a compound now that doesn't have a charge, has 0. So that means carbon must add up to -4 to equal 0. Well, that means carbon must be +4. If I look at the charges, carbon on the left went from 0 to +4. And oxygen on the left went from oxygen 0 to -4. If I think about how the only way that I can go from 0 to +4, my charge went up. That means I had to have lost 4 electrons for that to happen. For my charge to go down 4, I had to have gained 4 electrons. So this tells me instantly that if this one lost electrons, I go to oil rig, oil's oxidation equals loss. This got oxidized, and by the way, it is also the reducing agent or the reduction agent. And this tells me since it gained electrons, its reduction is gaining, but also I can see the charge 0 down to -4, the charge reduced. Then it was reduced, which means it's an oxidation agent as opposed to oxidization, which I sometimes say, sorry. So right away we can see the first one is indeed a redox, and right away we can see I've accidentally answered your question. But I will instead go on and show why the other ones, so the answer is C plus O2, and makes sense. It's very hard to go from 0 on the left to an obvious compound usually compositions are going to be oxidation, redox, and usually decompositions are too, but not always. So you have to check. So the answer here is obvious, but why are the other ones not? Why are the other ones not? Let's have a look. This is ammonia that becomes an ammonium, and it's a classic, it looks like a classic double displacement. So that means my N is going to go with my, my NH3. Oh no, this is not a classic. This NH3 goes up to NH4 over here, and it has gained an H, and this HCl essentially has combined with it. This is a composition. Well, this is a 0 here, which means we have to add up each of these charges to make sure. H is +1 with a nonmetal. Nitrogen's a nonmetal. So each one of these H's is +1, which means its charge is +3. That means to balance out, since this is a compound with no charge, it has a balanced charge of 0. That means if this hydrogen is +3 or +1 to each hydrogen, then this nitrogen must be -3. We know from our standard periodic table here, hydrogen's +1 with nonmetals, but we also know this is going to be +1. It's going to be -1 from our basic ionic compounds. The question is, what's going on here? Well, we have to start with something we know. Chlorine is usually -1, so we know it's still -1. Notice, did it change? No, it didn't. H is +1 with all nonmetals, and these are all nonmetals. So that means each one of these is +4, and 4 of them is +4. But that +1, did it change? No, it didn't. And that means if this whole thing adds up to 0, and I have -1 and +4, I have a charge total so far of +3, means my nitrogen must be -3 because this whole thing balances out to 0, and that -3 is the same as over here. So none of the charges changed, therefore there was no exchange of electrons and no redox. What about this one? Looks like it should be. This looks like a standard acid question. It looks like something got oxidized, so there should be, but we'll see. Notice that there's a 2- charge on both of them here and here. And let's look at the rules. Oxygen's -2 for each one. There's 4 of them, so we have -8. But remember that -2 as well. Which means the chromium would normally be +8 if this whole thing was 0, but it's -2. So that means the chromium must be +6. So that we have +6 and -8. We know that these, especially with a plus symbol here, there's 2 of them, but each one is +1. So that's all we should care about right now. Over here, we're going to look, and we have 7 oxygens, same rule, -2 each one. So it's -14. And normally this would be +14 on the right to balance it out, but we have a charge of -2, so it's +12. But now there's 2 of them, so we have to divide by 2, so it's +6 for each one. Notice this +6 is the same as over here. Notice this -2 for each oxygen is the same as over here. And this has not changed. Each hydrogen is +1 and each oxygen is -2, and that's no change from the left. So this is why this, even though it looks, especially with that oxygen gain, it looks like there should be an oxidation going on. That's usually a sign, by the way. When the oxygen goes up, it's usually a sign. But notice the chromium went up in proportion for the -2 charge. So that's why nothing happened. And you might say, why am I not multiplying by 2? Well, we're just looking at we're figuring out the charge within the compound. The 2 has little play on this charge. It would have a play on the total charge. For instance, if this had a 2- and I had 3 of them in front, the total charge on the right side of this equation would be -6. So if I had to balance, that 3 would be important. But within the compound, it's not. Or is this 2? So the total charge is -2. There's a -4 on the left side. But notice there's 2 here. That's +2. So there's only a total of -2 on the left side. And look at that. There's -2 on the right side. So this is already balanced in terms of its charges left and right. So that 2 only plays a role when you're looking at the whole equation. So let's have a look at this. if you look carefully, let's make sure that CO3, if CO3 appeared over here on the right side, we wouldn't have to figure it out at all. It would just stay as carbonate. But it doesn't. It went down to carbon dioxide and its charge changed. So we have to figure it out within the individual atom. There's oxygen. Each one has a -2, and there's 3 of them, so it's -6. We know calcium is in the first column, so calcium is always +1, which means for this to have a total 0 charge, because I don't see a charge outside, that means the carbon here is a +5. Over here we know chlorine is almost always a -1, and the hydrogen is always +1. There's no charge there. On this right side, each chlorine is -1, but there's 2 of them, so it's -2. Oh, sorry, my bad. Calcium, I don't know what I was thinking there. Calcium, of course, is in the second column, so it is a +2 because just a little brain fart, all group 2A is +2. And since this is -2 chlorine charge, the calcium must be +2 since there's no charge on this. CO2 here has a minus charge, I believe, if that's written correctly, which each oxygen's -2, and there's 2 of them. Oh, I guess it's not. Yeah, that's right. It's a minus charge. There's 2 of them for a total of -4. Normally, this would be +4, but we have to come out with a -1, right? I might have done this one over here. Oh, yeah, I did this one. If this is +2, then this is +3, sorry. So then -4, this would normally be +4, but we have a -1 charge, which means the carbon over here is +3, as it is over here. And then H2O is just still going to be +1 and -2. If we look, none of these charges over these individual things changed. So it looks like there's a lot of exchange going on in most of these, but there's not until that's why you've got to break it down using these rules. I'm not going to do the rest of them like this. We can go over them. A strong oxidizing agent typically is a strong reduction. It easily gains electrons. It will often have a positive reduction potential, and to prove this, all of these, as you see, become stronger and stronger oxidizing agents as it goes up. Look at what happens to their charge. They're going up and up positively until we get to +2.87. By the way, look at the bottom of this. There's lithium. Lithium, and you might say, oh, that's reduction. But it's a negative, which means it tends to go this way. Lithium tends to lose electrons, which is why we use them in batteries a lot now. Lithium is a great battery source. And it's amazing to me that it took us, 80 years, 90 years of battery use to finally use lithium. Very odd. Before that, we were using like copper and lead and nickel cadmium batteries. But we can see right here, lithium is one of the strongest reducing agents there is. So it readily gives away electrons. It also correlates to your periodic table. Things on the top right are going to be strong oxidizing agents. Things on the top left are going to be strong reduction agents. These guys are going to be wanting to give away their electrons fiercely, with the strongest at the top left, and these are going to want to take electrons fiercely. And it goes down as you go down left. It goes down as you go down right. So this is definitely always going to give away electrons readily, and this is always going to take electrons readily. And you might say, why is there no lithium fluoride batteries? There will be one day, but that fierce difference will cause a massive current, and a massive current can cause massive heat, which might cause a massive explosion. And you've heard all the mythologies about car batteries exploding. That's just propaganda BS. When they were first using these things, definitely, if you crack your battery, like if you run it into a brick wall and then somebody pours an ocean of salt on it, sure, they'll explode. You'd have to do ridiculous things to make them explode. And that's like a lot of things. If you puncture a gas tank and light a flame, it's going to explode. So don't believe any of the BS you hear. But yes, if I were to mix lithium with fluorine, I might have such a drastic current, as we have this massive voltage difference, as to be unvolatile. I have no doubt, as technology progresses, that that will be a future battery with massive potential, especially as they discover greater things, greater reductions. I also want to point out that your body and trees also use redox. The ATP in the Krebs cycle is all about reduction and oxidation. It's all about stealing energy for our body to use from chemicals. And that's what electrochemical is. It's getting electrical, converting chemical energy into electrical energy. Then, as people were dipping metals into solutions and connecting wires and creating batteries, we eventually said, hey, what happens if I run a charge? If I take an electric source and I run a charge through this, and I tamper with nature. And that's where this reverse happens, and we're going to get into electrolysis in a couple sections. Electrolysis reverses this natural process and forces things to happen that we don't want to happen. So, for instance, water does not easily break down, but if you run an electrical current through it, you are indeed going to produce hydrogen gas and probably oxygen gas. Another fantastic natural battery is the fuel cell using hydrogen gas and oxygen. They use it in rocket ships, and the waste is water. You might say, holy cow, why aren't we using those for cars if the waste is water? Incredibly expensive to build, and as you've seen from various explosions, slightly volatile. I don't doubt, again, that we will reach a point in technology. People keep measuring technology based on the knowledge today, but every day knowledge expands exponentially. Let's move on to what this question asks. A typical character, it has a positive reduction potential. No, no, no. When pitch blende is dissolved in nitric acid, so it would help if we knew what nitric acid was, it changes into this. At least we know the product now, and they kind of give us nitric acid right there, or they give us nitrate right there, so we can figure out nitric acid. What is the charge of the oxidation? So for this, we need to do a balanced equation. I don't mind answering this one. We need to do a balanced equation. And we need to keep our oxidation rules around, right? Good. Keep them like this, and like that, and crop, and zoom in. And we might keep that for a little bit, too. All right, so let's try to balance this equation. Let's zoom in a bit so you don't have to hurt your eyes. So they kind of give us the right side of the equation, which is nice. They give us part of the left side. But we have to figure out what's going on. It would help if we knew what nitric acid was. Well, nitric is a good thing is I ate something icky, which means nitric acid is formed from nitrate. Nitrate they've given us over here, and if we remember our Nick the camel, Nick has 3 consonants in it and 1 vowel, so that means it has 3 oxygens in it. And a negative charge, 1 negative charge. That's what the 1 vowel we use for, which means it's going to take 1 hydrogen, which means this is nitric acid. You can always look it up to make sure, and it's not a bad way to learn. But when you encounter nitric, sulfuric, oxalic, just know your Nick the Camel, ate a clam, supper in Phoenix rules, and it will help you determine the formula of these things. But yes, it's HNO3. So that means when I combine this into HNO3, you might say, do I need to know what happens to the other things? No, you don't. I also want you to notice, here we go, we don't have to come up with the individual charges of the NO3 because the NO3 is intact on the right side. We just have to know its charge compared to the hydrogen. We know that nitric on its own, nitrate on its own is -1 and hydrogen is +1. And we just have to use our rules over here. Well, oxygen is -2 for each oxygen. So that means we have to multiply that by 8, but I'll put the minus 2 down here. And it becomes minus 16. That means the uranium must be plus 16 because there's no charge on this, but there's 3 of them. So we have to take 16 and divide it by 3. 3 goes into 16 5 times with a third left over. So that means we get this bizarre charge of plus 5 and a third for uranium, for each uranium. Let's keep that around. I don't care what the other products are. There's water formed because the hydrogen went somewhere. And you might say, well, don't I have to balance? No, I don't have to balance unless they want a balanced equation. They just want the oxidation numbers. I can get the oxidation numbers in here. We know that each NO3 is minus 1. We also know there's 2 of them, so it's minus 2. We know that each oxygen is minus 2, and there's 2 of them, so there's another minus 4. Total of minus 6. That means uranium must be plus 6 because this does not have a charge outside of it. So it means it must add up to 0, which means for me to balance out that minus 2 and that minus 4 from the oxygen, minus 2 from the 2 nitrates, it must be plus 6. That means my charge of uranium went from plus 5 and a third to plus 6. Did the charge go up or down? If it went down, reduced, then it would have been a reduction. But it went up, didn't it? So that means it's got oxidized. If it got oxidized, that means oil, it lost electrons. How many electrons did it lose to go from 5 and a third to 6? It lost 2/3 of an electron. What is the change in the oxidation number? This is nice because they don't even want to know if it was oxidation or reduction. They just want to know the change. 5/3 to a 6 is a 2/3 change. These ones are annoying simply because they're fractions and simply because you're in the advanced class. Generally speaking, they don't throw these quarter fractions, third fractions at you. Most of your questions, though, like this one, will involve consulting your reduction table. The metals, they react as follows. So they're asking us to build a reduction table on this one. They're going to ask us to put them in the proper order. Which one's the strongest reducing agent? That's a little bit of a trick. So a strongest reducing agent is the one that is at the bottom of the list. The strongest oxidizations are so this is part of your advanced course as well. This table here is in descending order of oxidizing agents. The strongest oxidizing agents are at the top as it goes down. So they want us to order it this way. Bit of a trick. So what we're going to do is figure out the order in terms of reduction and then just reverse it because the reverse is in terms of oxidization. Kind of mean. So first we determine how they react. So remember that they're only going to react spontaneous from top left to bottom right, which is in order of reduction. Higher oxidization agent, lower, or higher reduction potential, lower reduction potential. Since there was a reaction here, and we can see the 2 plus went to 0, we can see that if I went from 2 plus to 0, my charge went down. That means PD reduced. And if this went from 0 to plus 3, it went up. The only way that could happen is if I lost 3 ejections. That means GA oxidized. GA oxidized. And PD reduced. The only way this can happen is if PD is a higher reduction potential, is above GA on the reduction table. So if I were to write it, notice that how many electrons did PD lose technically? PD, or gain rather, went from 2 plus, it gained 2 electrons, and it became PD0. We'll forget the numbers in front of it. GA lost 2 electrons, so we put it on the left side. It actually lost 3 electrons, and this is where the balancing that they did. And it became GA3 plus. Now, yeah, we would have to balance it technically, and that's why you would multiply the bottom one by 2 and the top line by 3 to balance out those electrons. That's how they came up with those numbers. But right now, this is just an important point. When it reacted, the PD stole these 2. You might say, no, it's 3. How can it be 3? Well, that's why they put these in front. The PD stole the electrons from the GA, and the GA lost its electrons. So that means this would be above GA on the reduction potential table. What about the next line? We mix CD and GA3+, which we can see over here, and there was no reaction. So if CD was up here on the top left and I mixed it with GA, and if CD was above it on the reduction potential table, there would be a reaction. But there is no reaction, which means that CD must be below GA. I would even argue that CD is written as a solid here, so it's probably on the right side, but regardless, it doesn't matter. It's below GA. Finally, we can see something happened here. Hg went from +2 to 0. Its charge reduced. So Hg2+ on the left gained 2 electrons and became Hg solid. PD on the left went from PD0 to +2. To go to do that, its charge went up. It had to lose 2 electrons. So that means we're going to write it on the, oh yeah, I've written it as reduction over here. If GE is losing the 3 electrons, it must be written over here. My apologies. And then PD over here lost 2 electrons, so it's written as PD2+ plus 2 electrons over here. Since this reaction did happen, it tells me that Hg2+ is above PD on the reaction table. Since PD is right there, that means Hg2+ must be above it on the reduction table. We now have an order, but notice it's in order of strongest oxidizing agents downwards, because these reduce first. They're the strongest oxidizing agents. But the question is tricky. It wants us in terms of the strongest reducing agent. The strongest reducing agent is the one that readily oxidizes first. That's the bottom of the list, upwards. So again, kind of some trickery. So that means my order of reactants, based on what's written on the left side of the table, would be CD, GA3+, because that's what reacted GA, because GA is up above, PD2+, because that's written in the reaction table, and then finally Hg2+. You can always confirm this if you have a very complete reduction potential table. You can always find, let's see if I can find some of them up here. By the way, these tables they have many more. So there's Hg. Let's keep looking. Don't think we're going to find CD on here, by the way. What else was on our table? GA, PD, and CD. And don't mistake lead for PD. So you can see it's not really that accurate, but here's a little trick you can do. So I'm saying this is the order. This would be the order in reduction potential, by the way, if we were going to write them in the right order from top to bottom on the list. But we can do this. Notice that we have charges on our reduction potential table, and that the higher the charge, the higher the thing is on the table. We can look up the reduction potential of each one of these. So I can just type in, for instance, well, reduction potential of Hg was written there. We know it right there. The reduction potential of Hg2+ is 0.85. So let's write that one over here. Technically, this one is going to be the top of the list, according to me. I could be wrong. Keep in mind, this could be a fictional scenario they're creating. So that means everything else will have a lower charge than 0.85. Let's look at GA's reduction potential. And let's just type in reduction potential GA. And we'll see if they give it to me. Sometimes you can find it. Yeah, it's negative 0.56 it would look like here. Here it is. But keep in mind, this is written as reduction. Oh yeah, that's written in the right direction because Ga3 plus is on the left side. So that so far we know that Hg has a higher charge, so it's going to be above it. What's the next one to look up? It's going to be, let's look up the Pd2 plus. And we discover this. And again, we have to assume these are accurate, right? That somebody's not just making up the numbers. And we see a plus 0.9. This would slightly jibe against our Hg. It would put Pd above it. So I should reread the question, make sure, or I should at least go and look up and make sure Pd is indeed 0.987. Yeah, it is. Let's make sure Hg plus is Hg2 plus, and then we'll go back and make sure we answer the question correctly. Hg2 plus is indeed point. Now some say 0.78, some say 0.9. So we have to be careful. See, you can get various things. Hg2 plus aqueous, and then 2Hg plus 0.9. So we're getting some slight conflict. It's saying it's 0.9. Let's see if I can pull up another more accurate one. 0.92 actually, yeah. So you can see it's dangerous using these reduction tables at face value because there can be slight differences. So obviously, in this case, if we go back to the question, it's not written as 2Hg plus. So we have to be careful which one we use, but for the sake of argument, let's use the stronger one. So that would indeed put it above Pd2 plus. And then finally, the last one we're looking up is cadmium, Cd. And we have to use our image again, and we can see it right here. Now, this would imply that it is actually above. Oh yeah, that's right. That's what it should be. See, this is in order of higher reduction potential down to lowest. So it is indeed. Let's see. I wrote it this way here, and CD should be below. So that means that there's a slight. Again, that's the problem with these questions because they're not always necessarily accurate in terms of the reduction potential. Let me make sure from another source. CD2 plus, negative 0.4. Let me look up again GA. And also always use the values on the left side. Ah, there we go. I should have looked up. Oh no, I can look up GA over here. Oh, actually, no, I should have looked up GA3 plus. It should be roughly the same, though. It doesn't really matter. Negative 5.49, yeah, it's still the same. Let me look up of GA. It should still just be the reverse. All right, well, just in case, I'm going to go back and we're going to try that question again, and we'll just analyze what's going on first, just in case. So we're going to go like this. And the problem with these theoreticals is they're often just written without accurate numbers. But let's go on. So this is definitely happening. And this is GA on the left. So that means if I was looking at the potential, the PD2 plus, since it's on the reaction side, is going to be on the left side. It's going to gain 2 electrons, and it's going to form PD solid. Since it's Ga here, the Ga is going to be down here, which means it's going to be Ga 3 plus on the right, plus 3 electrons. Since there was an exchange, PD2 plus must be above and to the left of Ga, because this is Ga. But this is a little bit different. CD is going to be reacting with Ga3 plus. It says there's no reaction. Ga3 plus is over here. It's on the left side. So, I mean, that doesn't mean, that means CD could be above and over here. All it means is CD is not over here. But CD could be up here or up here. We just know it's not down here. It could also be here. So that doesn't necessarily tell us, especially since CD is written as a solid. And all these are, you know, it doesn't always tell us that. But this does tell us that Hg does react with PD, and Hg is the one above it, which means that Hg2 plus is going to be above my PD here, and that PD2 plus is going to be above my CD. So that means this is going to gain 2 electrons and form solid. We just don't technically know where that CD fits in, because we're assuming that they're telling us, okay, since the Ga3 plus is on the left side here, this, if it reacted, it's here. If it doesn't, it's up here. The problem with that analysis with no reaction is it can be up here and up here as well. We just know CD in relation to Ga. Let's assume they want us to do it in order. That means CD is on this side, and CD2 plus 2 electrons is going to be that. Let's see if there's a reduction potential for CD2 plus. Yeah, there is. It's negative 0.03. So this would be negative 0.403. We're going to look up the reduction potential for Ga3 plus, because that's what we want. And the reduction potential for Ga3 plus is negative 5.49. So it would indeed be lower. So I guess we did do it right. And then we're going to look up for the reduction potential of PD2 plus. And the reduction potential of PD2 plus is positive 0.9. This is the only one that's going to be controversial. And then I have to look up the potential of Hg2 plus, and it's probably going to be the 2 plus, which is also a little bit higher. It's 0.92 or something. Let's see, 0.92, yeah. Which means this is the correct reduction order from top oxidization down, but they want the strongest reducing agent, which means we go in this order. So the order would be Ga3 plus, CD2 plus, PD2 plus, Hg2 plus, and sometimes they'll write it just as their metals. So when we look at the answers, which one matches the one I've just described? GaCd HgPd. Oh, they just want the one, the strongest one. So that's going to be the one at the bottom of the list. That's Ga3 plus, or Ga. There you go. And that's kind of logic, because PD reduced Ga, Hg reduced PD. So that means Hg is above PD, PD is above Ga, and no reaction happened here, so Ga is below CD. Which makes Ca the strongest reducing agent. Very tricky question, because you often don't ask the reducing agent, you ask the oxidization agent. Which of the following metals can be oxidized by Fe2+. So that's just a strict, let's find which one of these is in the bottom left of the table. So I'm going to pull up the reduction table. We're going to just shrink it like this. And we're going to look at each things in terms. We've got to find Fe2 plus. So if you look carefully, you're going to find Fe2 plus and 3 plus on your table. And it's usually quite as far as metals go, it usually gets oxidized easily. So there it is there. So in order for this can be oxidized, that means that this would have to go there. This would have to be reduced, and the other thing will be oxidized. So let's see which one is below right. Let's see if we see any. There's Cr. Cr is right there. Is Sn? Don't see it. Is Ag? Don't see it. Is CO? Don't see. I don't think CO will be on this list. But let's see if those are above. Oh, there's CO. So it's above. Sn, it's above. And silver, I know, is above as well. Silver's quite a ways up, I think. There it is. So that means because these are all above, they will not spontaneously react. But this one's bottom right, so that means this will reduce and steal the 2 electrons from this, which will go this way. You'll often see your teacher teach you this method, which is a circle going this way and this way, which tells you the reaction goes this way and this reaction goes that way. You can see it loses 3 electrons, 2 gains electrons. So if you were to balance this out, we'd have to write it like this. If the CRS is losing the electrons, we would write it like this from our reduction table. If our Fe2 plus is taking 2 electrons, we would write it like this. It would become solid iron. What's the problem here? This is gaining 2 electrons and this is losing 3 electrons, so we have to multiply everything up here by 2 to make 6 electrons. And we have to multiply everything down here by 3 to make 6 electrons. When I add up all these things, I get 2Cr on the left side plus 3Fe2 positive. That would be usually written above, right? Plus 6 electrons. And then I'd have the reaction on the products on the other side. And I get 2Cr3 plus, 3 plus, and then I'd get plus 3 Fe solids, plus 6 electrons. Notice there's 6 electrons left and right, which means we can get rid of them. Anything that appears on the left and right, we get rid of them. And this becomes the balanced reaction. Let's see if I can just put it in a whiter space. There we go. This becomes the balanced reaction. We get rid of the electrons, and that's how many, and by the way, this should be Cr there, not carbon. And that's how we do it. We take everything on this left and everything on this right, and we get rid of spectator ions and extra electrons, and later on we're going to get rid of water and other things. But when it's just 2 metals like that, it's a very simple balancing routine. You just have to make sure if something gains 6 electrons, something else has to lose 6 electrons. It always has to be balanced. This is balancing in terms of electron gain and losses. Okay, I think that's all the time I have for now. Let's just quickly page through and explain how to do each one. Very quickly, not. So we did that one. This one is measuring the volts, so you have to figure out is Ag or zinc, who's above who on the potential. Whoever is above who will take the electrons. Whoever is below will lose the electrons. Reduction always takes place at the cathode. Oxidation always takes place at the anode. Whatever's at the anode will lose its electrons and become, I think Ag is above zinc, but anyway. So let's actually just really quickly look. You'll find Ag way up here. You'll find zinc down here. Where are you, zinc? I know you're in here somewhere. See if we can get rid of some of the clutter. Yeah. Just not seeing it. This is my brain not seeing it, that's all. There it is, way down there. Which means Ag right here, when we find it again, is going to take one electron and become Ag solid. And zinc is going to go this way. It's going to lose 2 electrons, so that means it would be like 2 Ags if we were to balance it. But that means that over here at the Ag, this Ag is going to suck electrons from the zinc. The electrons are going to go up through the wire. Ag positive 1 is going to come up to this cathode, grab that electron, and adhere to it, become silver solid. This zinc, as it loses electrons, is going to dump into solution as Zn2 positive, and this anode is going to shrink in size until all the zinc is gone. And it's going to keep going that way. Now keep in mind, all cations will head to the cathode. All anions will head in the direction of the zinc. So that means all these nitrates will become negative, and once they lose their zinc, and they will head towards, that makes them an anion, they'll head towards the zinc cathode through the salt tube and neutralize that zinc plus in solution. The zinc plus will try to head towards the cathode, but it will meet NO3 on the way and combine into a neutral solution again. The Ag positive will reach the cathode, will grab the electrons, and will form solid silver on the cathode. Write an equation for the half reaction. Okay, yeah, that's that way. And then the zinc is going to lose 2 electrons. This is not an oxidation, that's a reduction. This is also a reduction. So this is not correct. This is correct. Ag will grab an electron, become solid. Zinc will lose 2 electrons and become an ion solution. What happens to mass electrode? The Ag increases and the zinc decreases. So I'm not going to answer these anymore. Which of the following is correct? Electrons flow towards, okay, so the electrons are being ripped off zinc, travel through the wire, and down to Ag. Okay, I have to go now. All these are answered in this fashion. Okay, so just really quickly, how do we solve these? Well, we just have to know the rules. Electrons flow from the anode to the cathode when it's a natural process. An oxidizing agent is, it's always going to be reduced, and reduction is not losing electrons. Reduced is gaining electrons. So oxidization agents reduced, reduction agents are oxidized. And you just got to remember oil rig. Which of the following reactions is spontaneous? You have to look up your Fe and your CO2 plus and see if they follow the left to right rule, and you do it for all your reaction side things, not your product side things. It's all about, if I mix these two things, will it be spontaneous? And spontaneity is all dictated by if it's top left going down to bottom right. Consider the following. The balance half reaction is, you have to balance the charges, figure out the oxidation numbers. Then you have to figure out which one is oxidized, which one's reduced. Then you have to separate them, just the reduced side of it, and figure out how many electrons are being exchanged. Then you have to do the oxidized side of it and figure out how many electrons are being exchanged. But then back to the reduction side, if there's any oxygen, for every oxygen you have to add a water to the other side of the equation, and you have to do it for either the reduction or the oxidization. Now obviously only one of these, there'll be oxygens on both of them. Then you have to add electrons to balance the, once you add water to one side of the equation, you have to add H plus to the other. This is another balancing rule. I should have included this in the rules. These rules are found in your textbook, and they are as follows. First, determine the oxidation numbers. Second, figure out who's oxidized and who's reduced. Third, write the half reactions, break them up into first the reduction equation, then the oxidization agent. Balance the equation other than O's and H's. So in other words, make sure your Cl's are all balanced, or anything that's not O and H. For every O on one side of the equation, add an H2O to the other. And this is for both. You do it twice, once for the reduction formula, once for the oxidization formula. Add H plus to the other side of the H2O that you added to balance. You add 2 H pluses for each water because there's 2 H's. Then now you've added a bunch of plus charges, so now you have to add electrons to make sure the charges are balanced left and right side of an equation. Then you have to, if one has more electrons than the other, you have to multiply one or both equations so that the electrons match. Then you add them together, top and bottom. Then you do a final check of all elements and all charges and to see if it's balanced. And that's in acidic solution. And for base, you do an extra step for each H plus that you have. Oh, by the way, once you add them all together, get rid of extra H2Os left and right. For instance, if I have 3 H2Os on the left side of my equation, 4 H2Os on the right, you can get rid of all 3 and there's just 1 left over. If I have the 6 electrons on the left and 6 electrons on the right, which I should, just get rid of them for the balanced equation. And then for the base, you do the same thing, but for each H plus, you add an OH minus on the other side, or on the same side rather, to both sides. And then you combine your H plus and H2O to form waters, get rid of the extra waters from both sides, and then just repeat step 9, add the half reaction together, and then do a final check. It's not that hard, it's just laborious. So I'll just show you an example of the dividing it into 2 reactions. Here's a full reaction. I figured out all the charges of the various things, figured out who got reduced, and marked it. So the Cl got reduced here and the Mn got oxidized here. And then you divide them into their separate reduction charges. And really, you don't include the electrons yet from the tables. You just write it like this. And then you go and make sure your Cl's are balanced and your Mn's are balanced. And then you go about count. So there's 2 oxygens, so I have to add 2 oxygens here. Oh, there's already 1 oxygen there, so just 1 water here. There's 4 oxygens here, so I have to add 2 waters because there's already 2 oxygens here. And then for the waters, I have to add hydrogen to the opposite side, 2 hydrogens here, so 2 hydrogen ions here, etc., etc. You can find examples in your book. And you can almost figure it out. You don't have to go through all that. You can figure it out just by saying, okay, what's interesting about this one is Cl is both reduced and Cl is reduced, right? So you can figure out what happens to the electrons. This has a 3 minus charge. Each O is minus 2. For Cl, it would normally be plus 2, but because we have a minus charge, it's minus 1. The Cl over here is 0, so it went from 0 to minus 1. Cl got reduced. For Cl to get reduced, there'd have to be electrons on the left side. When I see how many oxygens are on the right side of the equations, I'd have to add 3 waters on the right. Then I'd have to add, let's see, I'd have to add 6 H's on the right as well. Since it got reduced, the electrons should be on the left, but they're going to be disappearing. You're not going to see electrons in a balanced half reaction. Oh, this is just the balanced half reaction. So you're going to see ClO3 on the right. Yeah. Yeah, we should do it. Here we go. I'm just going to pull up a fresh one. So I know that Cl is going to get reduced from 0 to minus 1. So I'm going to just write Cl2. I'm just going to write the reaction first. I can see that there's not enough chlorines on the right. There's 2 on the left, so I have to write a 2 here. Oh, sorry, and that was a 3 minus charge, right? Which is ClO, 3 minus. Okay. So I have to write a 2 there. Great. Now I have to balance out my oxygens. There's 2, that's a 3 minus charge, not a 3 oxygen. So there's 2 oxygens now, so I need 2 waters. Let me go back and make sure I got the right equation here. Oh my God, that's O3 with a minus charge. So I even got the charges wrong. So it's really Cl2 to a ClO3 with a minus charge, which means 1 minus, which means that this is normally -6, and this would be +6, but that minus charge means it's +5. There we go. Now we can see the actual reduction. Come on, see, get rid of this. ClO3 and that means this has a +5. So it went from 0 to +5. It did not get reduced. It got oxidized and lost 5 electrons. For it to have 5 electrons, the first step is we're gonna balance the electrons. So we can see there's 0 charge here. There's a -1 charge here. Oh yeah, the first thing we have to do is balance the chlorines. So I have to put 2 there. That means there's 6 waters. So I'm going to put my 6. That's where the 6 H2O is coming from. Now I have to ClO3. Now I've created 12 hydrogens. Suddenly I've created a 12 charge here, 12 plus charge here, a 1, there's always a 1 negative here, and there's 0 here. So now I have to balance out my charges. So I can see that I have +12 -1, so +11. So I have to balance it out on this side with +11 electrons. Oh wait, there's 2 of them, so it's +10 electrons. Come on, come on, come on, come on. Great. Now I have to make sure all my things are balanced. 12 hydrogens, 12 hydrogens, 6 oxygens, 6 oxygens, 2 chlorines, 2 chlorines. Charges, 2 minus +12 -10, so that's 0 and 0. So this is my balanced equation. The only one that matches, that has 10 electrons on the right, is this one. And it's exactly as we've written. 12 hydrogens, 6 waters. Use the following to answer the question. You got to figure out which is above on the reduction. Then you can answer the question. Who is reducing who? You have to find PB and Zn on your reduction table and figure it out. We already know from before that Zn is right about here. How come I never find Zn? It's really frustrating. We just have to find out where lead is. Well, lead's up here. And you're allowed to look at Pb2 plus, even though they're saying they're both solids, because, as you can see, they have ions in solution there. So it's quite clear from the table that Pb will take the electrons from zinc, which means the zinc will shrink and Pb will grow, and the electrons will go this way. You can also add the cell potential. So in this case, Pb is -13 and zinc will reverse. By the way, when you add cell potentials and they're positive, it's usually spontaneous. So we know that this is plus 0.74 when it's reversed, -13, we just add them together. We get 0.61 volt potential positive. That's why it'll make an effective battery, creating 0.61 volts. If I tie them all together in parallel, I can create larger volts. So that means that would be the answer to this. Oh, how come did I add it wrong? 13 and, oh yeah, no. So that's plus 0.74 negative 0.13. Add them together. I get 0.61 positive volts. And they're saying that. I must be having a brain fart somewhere. Did I get zinc correctly? Oh, 0.76. Sorry, I was looking at chromium. So 0.76. There's my brain fart. Minus 0.13. I get 0.63 positive. It's never going to be negative, by the way, if it's happening spontaneously. It's always going to come out positive. Which of the following should be used cathodically to protect an iron sculpture? Anything that's below it on the reduction table, usually magnesium is lower, will protect iron from rusting. They use that in cars. They also run an electric current through cars. To protect it, use the following diagram. So we have to figure out which one is... Oh, hang on. Oh, boy, it's a busy day. So in this one, what we have to realize is they're asking specifically about what happens to CR and the silver. So you have to figure out who's above who on the PB table. Now, I can't spend all the time answering all these questions. What happens to pH at each electrode? That's a great question. So you're going to have to look at what's going on in terms of hydrogen, which is going to be affecting the acidity. And it should be one is going to become more basic and one's going to become less. So one's going to become more acidic, one's going to become less acidic. And it's very much based on the reaction as to what is created. And that's covered in your textbook as well. Ion movement, so that's within solution. And that's a common question. Anions move towards the anode. Cations move towards the cathode. So you just have to figure out who is above who on the potential table to figure out who's being reduced and who's being oxidized. Which of the following best describes a car battery? As it's being recharged, so it's getting energy from the motor. So the motors can turn kinetic energy into electric energy, and that becomes an electrolytic cell. The battery, without being recharged, is an electrochemical cell. What are the most likely products of electrolysis? This is an interesting question. So electrolysis is when we start applying electricity to solutions and going against nature, forcing them to do things, creating products we want, like certain metals. The problem is, when it's in solution, water is in there. And we have to look at what's called overpotential of water. But essentially, when you look at water, or anything that's mixed with water, we have to go to our potential tables again. And we have to notice, oh, wait a minute. Water's in there. Water's in there in two spots. Water's here. And water is here. And then we have to look at whatever's in there. Let's say chlorine is in there. And actually, chlorine's a bad example because chlorine always wins. Let's say bromine is in there. No, bromine always wins too. Let's say, okay, let's just say iron is in there. And then we got to go down to this one and we're going to say, okay, and aluminum is in there. The top two are the things that are going to be reduced, and the bottom two are the two possible reductions. You have to look at the difference. If these are the two reduced, ignore this is not part of it. You have to look at the difference between this 0.82 and this -0.41, and this iron and this one down here, and see how much different voltage. And then you have to do the same with this and the bottom one, and this and the bottom one. If whoever has the smallest voltage difference, and my guess is it's going to be this one, so we can see it's 0.77 and 0.41, so it's going to be 1.8, and this is going to be much higher. It's probably, that means that this is going to be at the cathode, but water is going to be at the anode. So you have to look at the difference in their electric potential, because sometimes water ruins the process, essentially. The only exception to that rule is bromine and chlorine. Bromine and chlorine will always be at the cathode. So then we just have to figure out how close is Mg to water, how close is I2 to water, and how close is Mg to I2. And you can see that, so, you know, sometimes they're saying it's just water being electrolyzed. Sometimes they're saying it's magnesium and oxygen. Sometimes they're saying, oh, no, the Mg and I2 work. and the H2. So if we just look very quickly at Mg and I2, we'll see Mg here. Let's get rid of some of the clutter. And we'll see I2. Oh boy, I think I2 is going to be way up. Right there. 0.54, and that's going to be the reverse, so that's a big negative. There's a darn good chance that this is going to electrolyze with this as opposed to this and this. And that's because these are closer. So my guess is iodine and water. And it's going to be the, since this is the negative, it's going to be the hydrogen side of the water, because the hydroxide or the oxygen side is the negative ion. So we have the negative ion up here already, so it's going to be the positive ion. So my guess is it's going to be hydrogen and iodine. Okay, let's keep going. We've got an aqueous solution of CSO4 is electrolyzed. So again, it's in water. Which of the following happens at the mass of each electrode? Well, we have to be careful, because if water is interfering, oh, both are copper electrodes. Okay, so the copper is coming off of one and going to the other. Which of the following would correctly describe the change in the mass of each electron in the CO2 plus solution? Well, I believe that this is increasing. I believe this is going to stay the same. And this is going to decrease. So I'm going to guess it's that. The anode's definitely not going to increase. Oh, fire alarm, sorry. So really, why is this so? What happens in the electrodes is the ions go towards one or the other, and they usually add to the cathode, so the cathode grows. And then they get the source of the electrons from the anode, so usually the metal gets stripped of electrons and dumps into solution as an ion, and so the anode shrinks. That's most of the time. Now when they're inert, however, which is this mass of each aqueous solution is electrolyzed. So when it's electrolyzed, you have to go the reverse direction. However, even in the reverse direction, cathode is the source of reduction, so it's still going to do that. So we're essentially breaking apart this here. It's going to create a positive ion of Cu, 2+, and positive ions, or cations, always go to the cathode. So the cathode will increase in size. So my guess is what we're trying to do here is create copper wire. Operating in the electrochemical cell, the anions always migrate towards the anode. Cations always migrate towards the cathode, and the wire is always just the source of where the electrons move. The ions, anions, and cations stay in solution. And yeah, through the salt bridge. Consider the following overreaction electrochemical cell. So we have to do, they're telling us that Ag does indeed is reducing, is the oxidizing agent, and Cr is indeed oxidizing. And you have to look up their potential in the table. You do not consider the 3. You do have to make sure to see how many electrons are being reduced, but the voltage is not affected by the 3. The current is. So the voltage is just looking at the reduction potential of both these things. Analytic process is used to purify impure lead. So in that case, your cathode will always be pure lead, because you're trying to take an anode of impure lead, strip it of electrons, it'll dump in solution, then the lead positive ions will head towards the lead cathode and adhere to it. So your anode is going to be the impure lead, and your cathode is the thing where you're trying to make pure. Pure lead, impure lead. This is a process, a power supply of we're trying to cover this key in something. Depends what's in solution. We're trying to cover it in copper. So by running a charge through it, we're going to create copper 2 plus ions. The negative and the positive indicates the direction of electrons. So the positive is going to pull electrons up here, and the negative is going to push electrons down. When the electrons come down, the copper 2 plus will float up to the key to grab the electrons and turn into copper solid. So this is technically the cathode, and this is technically the anode, and this is how we do electroplating. So the half reaction is the CO2 plus will grab 2 electrons and form copper solid. And that's exactly what will happen to the cathode. This is just going to go over and grab whatever's coming off of this electrode. This would be a pointless process, although it's a good point. You should actually check first what's going to happen at the potential difference to make sure this is possible. But this is the goal. I know that. So we should really check the potential of water against both copper and sulfate. A real quick check shows copper here and sulfate. Yeah, so copper is down. Let's see if I can release it. Sulfate's up here on this side. That's not what you want. Or we could just look up the potential of sulfate, although I guess you're not supposed to. Reduction potential of SO4 2 minus. And it is minus 0.93. Let's see if it's on our table. No, it's not. Minus 0.93. Minus 0.66. Yeah, I don't see sulfate on there. So the normal thing, obviously, would be probably that sulfate's going to be top left and copper is going to be bottom right. And the electrolysis reverses that direction. Oh, there it is. Right there. Great, they're right close to each other, which is probably why you use it. So the water is going to be up here and down here. And because these are very close to each other, right there, we can see that they're so close that this is not going to get interfered by water. So indeed the copper will adhere to it. He's trying to figure out the volts for the half reaction, so he did a recording. He recorded this with copper and then did this with, saw that there's no reaction here. Based on the above, the PD cell is this. So you'd have to look up the copper between PD2 plus and copper. So again, that's all about looking up your potentials. I'm going to go back to the question. So that means AU would be above it, HG would be above it. So we have to look at AU and HG because obviously PD2 plus is not going to be on our chart. We know it reacts with Cu2 plus, so it's going to be above Cu2 plus but below AU and HG. So that gives us roughly a range. So it's going to be above Cu2 plus. Cu2 plus is right. C plus. Well, we can use the Cu plus, so we know it's going to be above it. And we also can say, yeah, we should really use Cu2 plus. So let's see if there's a Cu2 plus in there. It's odd not to include Cu2 plus. There it is there. I mean, you can reverse it and say it's 0.3. Now let's find gold. Let's just find gold and mercury. There's mercury. And there's gold. So that means it's going to be below those. And it's going to be on the right side. So it's anywhere from 0.3 to 0.15. So it's going to be 0.65 or less. Is the idea, I think. Probably that's the answer. Just more analysis of it, just spend more time on it. Principal function of a fuel cell is produce fuel, electrolyze fuel, produce hydrogen, produce electricity. Almost every electrochemical process is converting chemical energy to electricity. Written responses. So for titration, you should balance the equation first, but realize that they give you the amount of moles of MnO4. The K is going to be irrelevant. Once you balance the equation, you can figure out how much peroxide, H2O2, will mix with this. But you'll be able to figure out the moles of the MnO4 from this, and depending on the ratio, you can then figure out the moles of hydrogen peroxide. Oh, they give the reaction. So 5 hydrogen peroxides with 2 manganetes produces 5 oxygen. Identify the reducing agent. So which one oxidizes? So this Mn is 2 plus here, and over here it is plus 6. So it reduced. So it oxidized. It's not the oxidizing agent. And so that means the H2O will be the, it reduced. So it's the oxidizing agent, which means the H2O will be the oxidizing agent. Calculate the concentration H2O. So whatever you discover for the manganate moles, double it, and then divide by 5, and that will be the moles of H2O, and then divide that by that milliliters to get the concentration of H2O. Describe an observation might be seen in the reaction process. I believe manganese is purple. So we'll see it clear until it's all totally reacted, and then it starts turning purple, I believe. A reaction occurs with copper metals dropped in solution of silver nitrate. Great, that means copper naturally reacts with silver. Write the balance formula, so you have to figure out who's above who. Copper is probably going to take electrons from the silver, but you never know. It all depends on who's up above. So here's Ag, and copper's below. So it looks like Ag will take the electrons. You can write the balanced equation because the copper metal will become an ion, and the silver nitrate will become solid. The nitrate will play no role at all. It won't be in the equation. Describe one observation that might be seen as the reaction progresses. The copper metal will shrink as it gets stripped of electrons. On a silver spoon, there we have a black tarnish can be removed spontaneously by placing the spoon with aluminum. So that means aluminum is going to remove the Ag, or the Ag ions here are going to become solid metal, and the aluminum is going to become stripped of electrons. Write the equation of the redox reaction. That's not too hard to do. Write the balanced equation for the half reaction in basic solution. So follow the steps I described. Balance the following reaction in basic solution. So follow the steps I described. Using a copper anode and an inert copper cathode, predict the half reaction. So electrolyze means we are running a electric current through it. So it's going to be the reverse direction of what would happen between copper and chlorine. The inert carbon has no role at all. It just stays carbon. A silver, aluminum, nickel. So when you have multiple things, you have to find out which one's higher on the reduction table and which one's lowest on the reduction table. And those will all reduce and oxidize first, and then after one of them is gone, the other one will. Oh, so you have to figure out which one has the difference potential between Ag, aluminum, and nickel. The significant risks to operate this would be, it's a good question. Is there anything poisonous in here? Nickel, aluminum, and silver? Good question. I have to think about that. Electrolysis means we're reversing the process, so we're trying to break this apart. Products are oxygen gas and hydrogen gas. That means water is closer together on the reduction potential than lithium and fluorine is. Write the anode half reaction, so we can just look up the water on the chart and look up the cathode, see which one's higher reduction. So on the water ones, this one will reduce and this one here will oxidize. So it will go this way and this one will go this way. Minimum voltage will be the difference between those two, and that's it. Pretty straightforward, but a lot of work. This is a long assignment. I encourage you to do the work on it. It's all about just following those main steps to do it. Sorry it's a long video, but there you go. Play it at double speed.